Welcome to Pomodoro Joe for Sunday, July 23rd, 2023. Today we're doing LeetCode problem 894, all possible full binary trees. This is a medium problem. Given an integer n, return a list of all possible full binary trees with n nodes. Each node of each tree in the answer must have node.val equal to 0. All right. Each element of the answer is the root node of one possible tree. You may return the final list of trees in any order. A full binary tree is a binary tree where each node has exactly 0 or 2 children. All right, so we don't have any just one child nodes. Okay, got this example here. And it looks like we've got some symmetry going on. That might help us later on. All right. So let's put 25 minutes on the Pomodoro timer and we will get started. Okay, so it looks like we'll take one node. So given n, we can have one node at the root, and then let's see, if we only have one n, or if n is equal to 1, we only have one node, we can just return that node. If n is 2, that's actually impossible because we can't have a full tree with 2 nodes. It has to be at least 3. Well, it has to be at least 1. Then the next sort of quantum would be 3. You have 1, 2, 3. Interesting. All right. I think the way I'm going to do this, I'll take a clue from yesterday's video where we had to do different moves of the knight piece in a chessboard. We used some dynamic programming. So let's do the same today. So let's see. We'll have some dynamic programming, so some list here. Let's just do this. dp, it's going to be an empty list to start with, but we can actually precede this with some values. So let's make dp of some n equal to the list of all the trees, basically the answer to this problem, all the trees that have n nodes. So let's do this here. Key is equal to node count. And value, it's going to be equal a list of all the trees with that node count. All right, so let's see. We need to go up to n. We're trying to find basically dp at n. So we'll start this off with just nones. And we'll just do none times n. I think that should work. All right, so we're just going to fill this with none. Actually, we want to be able to index n, so it's going to be times n plus 1. Now let's do it. Let's be super safe. All right, let's do it this way. So we'll just have nones for all of our possible n's. Okay. Now we do want to precede this, or basically fill this in with a little bit. Oh, and I'm not making this a dictionary, so it's not really the key. This is an index. All right, so the index represents the node count, and the value is the list of all the trees with that node count. All right, so our dp, well, dp of 0 is none. You can't have any trees with no nodes. dp of 1, so this is one tree node. Because that's basically n is 1, we can return just the root node. That works. And then n as 2, we've already discovered we can't have any complete trees with just 2 nodes. So that's also none. And then n of 3 would be a tree node with 2 adjacent tree nodes. But I think we can build that up from this point. All right, so let's actually say dp is equal this. Well, no, we can't say it's equal to this. This is what we want, so we'll say dp at 1 is equal to this tree node. All right, so dp of 0 is still none, dp of 2 is still none, but dp of 1 is this tree node. And actually, because this is going to be a list of all the trees, we actually need to make this a list with just one tree node in it. Okay, so this sets up our basic dynamic programming. This is our sort of seeded dynamic programming. Everything from this point forward, we'll just have to refer back to these smaller trees. Okay, let's fill in the rest of our dynamic programming array here. So for every I in range, let's see. Well, we've already got 0, 1. We can go from 2 forward at this point. So we'll go from 2 to the end, and the end will be n plus 1. All right, so now we're going from 2 up to n plus 1. This is not inclusive, so this will give us index n, which is exactly what we want to return. And then for now, I'm just going to pass. Let's go down to the end here. Make sure I don't forget to do a return. So we'll just return our dp of n. All right, that's our goal. I actually like having results, so let's make sure that we do this. It's a little bit slower. It might take a little more memory, but in case I want to print this out, it's nice to have this. All right, so let's do that. What's next? Well, let's see. For every I in our range, so we're basically filling in this dp. We're going to go dp of 2 is equal to something, then dp of 3, dp4, dp5. Okay, so what is that going to be equal to? Some set of trees. So I'll have a tree list. That's going to be equal to an empty list to start with. We'll go through, build up that tree list, and then if we have this tree list, so if it's not empty, then we'll fill in our dp at this value. So let's do that here. Actually, let's make sure it's not empty. Well, we'll get to this. I'm jumping ahead of myself. We'll get to this. All right. So we have some empty tree list. This will be our list of all the trees of dp at this I. So this is the list of all trees that have I nodes. All right. So for this, we'll have some node count. And that node count is really just I, well, actually it's I minus 1. So, all right, what we're doing, we're going to grab this node. This is a root node. We'll have some root node. And then what other trees can we build for our left and right branches after this root, or left and right children of this root node? All right, so the remaining nodes, let's actually call this remaining nodes. Well, we have I total nodes. One of them will be the root node. So the remaining nodes, after we remove that root node, we have I minus 1 nodes to build both the left and right trees. Okay, so now that we have our remaining nodes, we'll go through every single possibility of splitting up the remaining nodes between our left and right branches. So that's what we'll do here. We'll take every possible combination of left and right. So basically left will have 1 node and right will have remaining nodes minus 1 nodes. And then left will have 2 nodes and right will have remaining nodes minus 2 nodes, and so on and so forth. All right, so let's do that for every j in range. And we will start with 1 node on the left and the remaining nodes on the right. So we'll start for I, or j. So for j in range, from 1 to, let's see, what's our remaining nodes? It's just remaining nodes. And we do have to add 1 to it because we want this to be inclusive. We're just going to divvy up all the remaining nodes between our left and right branches. All right? Okay, so I could call this left and right. I can call it A and B. I'll call it left and right, but I don't know. If we call it left and right, then we can't take advantage of this symmetry. As you see, there's like this whole tree is just a mirror image of this tree. So I don't know, I'm hesitant to call it left and right, but I'll call it left and right. All right, so our left, and these are going to be just all the different trees that we can assign to the left tree. So these are options. This is not going to be a single tree. This will be a list of trees because we're going to be using our DP to grab that list. So the left options, that's just going to be our DP for this current I, or sorry, this is J now. All right, so we're going to be grabbing our tree out of our DP for the left branch, and that left branch just has J nodes in it. And the right options, that's the remaining nodes. So that's going to be DP of, well, these remaining nodes minus the nodes that we used on the left side. So let's see, remaining nodes minus J, because we've used j nodes on the left, we only have remaining nodes minus j nodes remaining on the right branch. All right, so now we figured out our left and right branches. Let's see if either one of those, these are the options. Again, these are lists of trees. So there's a set of trees in this left options and the complementary set in the right options. So if we're looking at, let's see if there's an example here. I guess if we're looking at this one, then our left options will contain this set of trees, or this one tree, and our right branch will contain this tree. All right. So we have these different options. If either one, though, is null or none, we don't have options on that side, that means we can't have a child of our root node, and we're not allowed to have an empty child. It has to be a full tree. So if either one of these is none, then we're done with this set of options. We just continue. All right, so if either one of these is none, we cannot use the other option because we'd end up having I guess an empty child on one side. So we'll just continue. Now, if we do have options for both the left and right branches, well, now we have to do all the permutations of those two sets of options. So for every left in left options, and for every right in right options. All right, now we can build a new tree. So we'll have some root node, it's just tree, and its value has to be 0. And let's see, its left will be left and its right will be right. Am I getting this right? Left, yep. So we'll build a new tree starting with this root node and putting the left and right branches into this node. All right, now that we have this option, all right, this can be a new tree in our tree list. So let's see, tree list dot append this root node. Okay, so we're building this up slowly. We're going through, we're building our DP. So now we actually have to take this tree list and we have to assign it to our DP. So if we have a tree list, so if tree list, let's see, if we don't have it or if it's empty, then there are no options for this DP. So if we don't have a tree list, then we'll set the DP for this I equal to none. We could probably skip that because I think it's already set to none, but let's just be safe. Otherwise, okay, we've got some list of options for this DP. So then this DP at this I is equal to our tree list here. All right, so we'll go through basically starting DP at 2, go to 3, 4, 5, 6, 7, 8, up to n, just building up what is the DP for this tree or this number of nodes. Eventually we'll reach n nodes. All right, so let's try this just to see if we make any typos here. Yep, let's see, left option is not defined because I called it options plural. All right, let's see if I got any more typos. Okay, so this works. Let's submit this and see if we can pass all the tests. And we pass. Let's see how we did here. And we crush it. All right, we're beating 100% for runtime and 50%, no, 80% for memory. Holy smokes. That is killer. Man, that's one of the best scores I've ever gotten. Well, it's the best score I've ever gotten, but I've had a couple other hundreds. All right, this is awesome. I'm super psyched. Okay, well that is it for me. Hope you enjoyed this, hope you had fun, hope you learned something. Oh, let's go back, let's do a quick review. All right, once again, we're building up some dynamic programming array where each value, I should say each index, represents the number of nodes in the tree, and each value is a list of all the different types of trees that we can build with that number of nodes. So we'll start with 1 node, 2 node, 3 node, 4 node, so on and so forth, up to n nodes. And again, we can do that because our n node tree list is dependent on our earlier node tree lists, or n-1, n-2. All right, we initialize our DP with at least one node for our DP of 1. Then we just go from 2 to n plus 1. Actually, this is just 2 to n, but we use n plus 1 because we're in a range here, which is not inclusive. We have some set of options. How many different trees can we build with this n? To get that, we have to go through basically splitting the n into different halves, the left half and the right half. So we'll go 1, 2, 3, 4, up to however remaining nodes we have. So we'll grab one node out to be the root node for this particular tree. Then we'll just split the remaining nodes up between the left and the right. Then for every left and right option, we find all the different permutations of left and right options. Then finally, we'll put all those options into a list and then put that into our DP for this number of nodes. Finally, at the very end, we just return DP at n. All right, that is it for me. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code. Although not better than this, because code is the best.